Hello, my name is Drew Drakowski, and I'm president of Pitaro Systems. I recently gave a presentation at the AUVSI Exponential in Denver at the Public Safety UAS Symposium entitled Traffic Crash Reconstruction, the How, When, and Why. The presentation was intended to cover the use of drones for traffic accident investigation and reconstruction. I've had several people who have asked me for copies of my presentation who either were able to make it or who maybe couldn't make it and were curious what I presented about. In looking over my presentation, I realized it was mostly pictures. So in order to get across the information I wanted people to hear, I decided to make a slideshow and present it this way. So here's the presentation that I gave in Denver. A little information about me is I'm a current police officer with 18 years of experience. I have been a traffic crash investigator for 16 years. I currently work in my agency's traffic unit where my primary responsibility is to investigate serious injury and fatal crashes. I have 5 years experience with unmanned aircraft systems. I'm a remote pilot for my agency. I was also recently certified as a mapping scientist through the American Society of Photogrammetry and Remote Sensing. I also stay active in several different committees, one of those being the Aviation Committee for the International Association of Chiefs of Police. So to get started, let's talk a little bit about how we have always investigated traffic crashes in the past. When I started doing this, we were using everything with measuring tapes, whether it would be tapes on the ground, whether it be roll tapes. Eventually, we graduated onto total stations, and honestly, my agency today is still using total stations for most of our measurements. A lot of people will say that once you get drones, you can throw your total station away, and that's simply not the case, or at least has certainly not been my experience. All of our aerial imagery in the past has come from fire trucks. That we were lucky enough to work very closely with our fire department. They would bring a fire truck out and let us take aerial images from that. This was really good for demonstrative purposes during courtroom presentation, but it wasn't useful for metric and measurement sort of use. That I could show you the picture up here and explain that these were tire marks, that there was striations in them, and what that meant as far as the dynamics, what was going on with the vehicle. But I couldn't tell you exactly how much distance there was between either one of those tents. The problem with fire trucks tends to be that we can't just put them anywhere. They can usually be set up one time. We can take aerial images for whatever the ladder can reach. But we're not going to put these in people's backyards, and the firefighters probably aren't going to let us move these multiple times because it just takes so much time and energy on their part. So this is what we had. So now what are we moving on to from there? In 2014, I participated in a cooperative research and development agreement with the National Institute of Justice. At the time, NIJ was very interested in using drones for faster traffic accident clearance. We've all heard the case studies, and we've heard many times how drones increase the efficiency of the investigation on scene and the accuracy of the product. In 2014, that wasn't the case. We didn't know how drones could be used or if they would be useful. A big part of this study was determining the appropriate level of overlap, testing different altitudes for image resolution, and developing methodologies for collecting this imagery and checking to see what our actual errors were, and then comparing those accuracies with current methods, and then timing that to see what the efficiency was compared to current methods. All of this culminated in several different mock traffic accidents where we did head-to-head comparisons with a normal crash team investigation. In those different studies, this mock accident would be set up, and the traffic team that we were essentially having this competition against would get timed from when they could open the doors to collect all the equipment out of their vehicle, set it up, collect the measurements that they needed, pack all their equipment away, and shut the door. So essentially door to door. And then the same time was taken for the drone. How much time did it take to set it up, to mission plan it, to fly it, to break it down and put it away? Those times were compared. And in these particular cases, these are very level traffic crashes, very straightforward. The drone was completing it somewhere in about 18 to 24 minutes. The traffic team coming out, who knew that they were in some sort of a competition, was right around an hour to measure the same points. So that was the first comparison. The next one was with accuracy. We actually found that the accuracy was very comparable. We were within a millimeter or two of what the traffic team was collecting. So essentially same. And then the other thing to note is that the traffic team, because they were probably in a hurry, missed a couple of points that they did not measure. And that's not uncommon. We miss points at every single traffic accident scene we go to, whether it be because we forget to measure it, or whether it because we didn't know that it was important at the time. And so we find out about it later, the scene's already gone, we can't go back and measure it. So what's nice about the photogrammetry is we can always go back and do that. The accuracy findings of the NIJ research was published by SAE. The SAE paper number is there on the slide for you, 2015-01-1426. If you're interested in getting a copy of that, I'm going to have an email address at the end of this presentation. Feel free to shoot me an email, and this is government research, so I'm happy to share it with you. So this is the kind of imagery that we're probably used to seeing from drones. What's nice about this kind of imagery is that it allows us to see things from different perspectives, that this was a traffic crash where an officer made a traffic stop, and during the traffic stop, the subject pulled a weapon out on the officer grabbed onto the weapon, and they ended up getting drugged down the street. As they went down the street, they went through the front yard of this house, they hit the side of the house, and they went out into the roadway and hit the other car that you see inside of this adjacent street. I can tell you that whole story. I can show you some ground pictures, but getting some aerial imagery and seeing down the street, seeing through the trees is helpful. I get a lot of questions from first responders about whether we can use drones to collect imagery at nighttime. And the answer is yes, that generally speaking, there is enough light for us to collect some pretty good images. This was a crash that happened obviously at nighttime. This was a vehicle that lost control, went off the right side of the roadway and hit into a tree. Once it hit the tree, it overturned, and the driver in this case died. You can see the significant impact that occurred on the driver's side. This is good for several different reasons. I mean, first, I can show imagery I'd never be able to get otherwise. I couldn't put a fire truck in this person's backyard to collect this imagery. And it also lets me get directly overhead of the vehicle to see exactly how much intrusion there is, that when I'm trying to explain to a jury how much force was involved in this crash, this is the kind of picture that helps me tell some of that story. So you've also probably seen a lot of ortho photos that have been shown online or in different classes. This is an ortho photo of the daytime scene I was showing you earlier where the officer was drugged down the street. I've got my laser pointer out on my PowerPoint here, but this is where the actual traffic stop took place. When the officer was drugged down the street, he was drugged past this street. You can kind of see where there's some tents in the road where they went across the road. At this point, the officer was able to pull the suspect out. They both fall out of the vehicle here. Vehicle kind of ghost rides through the front yard and ends up hitting another vehicle over here and coming to rest. So this is the kind of imagery that we wouldn't be able to get any other way typically without drones, but it lets us tell the entire story, even though we're not necessarily using this for measurements at this point. Here's a second example. This is the nighttime scene. Again, this is where our vehicle lost control, was heading southbound on this road. We think that they tried to avoid the center median, so we overcorrected to the right. When we did so, the driver lost control, went off the road, went through the snow sideways, hit into this tree, and then rolled and went into the front yard. Again, this is at nighttime and with snow. It actually shows up very well when we're talking about an ortho image. So you've seen some of the pictures and the ortho photos, but why is it that we're using drones for crash investigation? Well, the first reason I would say is for efficiency, that it does save us time in doing scene diagrams for us to use drones instead of traditional methods. That said, please, please, please do not go to your bosses and tell them that you're going to be able to map a scene and clear it in 15 minutes or a half an hour or an hour. It doesn't mean that we're not going to still do all of our normal traditional ground processing that we would. We still have to identify the evidence. We still have to take close range pictures of it. We're not going to get pictures of fibers or skin or blood on the roadway like we would on the ground taking these pictures from the air. So we still have to do all of the normal evidence processing and collection that we would on the ground. Where this saves us time is when we go out to measure the scene. This is a crash that we investigated that was on a major thoroughfare through our city. It has 3 lanes in both directions. For us to have measured this with a total station would have easily taken us probably 2 to 3 hours if we wanted to get all the lanes and if we wanted to get all the sidewalks, etc. This was a motorcycle that was heading down the road, lost control in the center of the street, rolled into the center median. The driver, unfortunately, was not wearing a helmet and was killed at the scene. As you can tell from the image on the right, this was in the middle of the day. This was right around 1 o'clock in the afternoon on a weekday. We had traffic absolutely snarled. We were trying to break down both lanes break down 1 lane in both directions. What I asked my supervisor in this particular case, this is actually the one that really got us motivated as a team to show what the capabilities were. I asked my supervisor to give me 5 minutes after we had the opportunity to mission plan all of this to shut down the entire roadway so that we could map it and then open the roadway again. So this is the map that you see on the left that was taken from taking the overhead imagery with the drone and what it would have looked like had we tried to put an ops route in the scene to try and do this with a total station over there on the right. Which brings me to the second piece of this, is safety. So it's the safety of the officers having to stand in the roadway, and if we can reduce the amount of time that actually occurs, the safer it is for all of the officers on scene. Additionally, the less time that we spend in the roadway, the less time we're snarling traffic, the less amount of time we're going to have for people to crash into each other as they're watching what we're doing. So it's safer for the public as well. Accuracy, as I've kind of talked about with the NIJ study, what we're finding is that the accuracy of using drones is the same as if we were using our total stations. We're still going to get within a few centimeters to a couple of inches, depending on how you're doing this, and it's going to be very similar. Last part of it, the one that's really the most important to me, is the evidence. It's all about the data for me. I mean, we can get so much more data from imagery than we can with our traditional total stations. Instead of taking individual points, we can now get point clouds. It's also, going back to that efficiency piece compared to using a laser scanner. We can cover a much bigger area and get far more data than we could with taking multiple scans. So this always brings me to, when I come to a traffic crash, is what is it we're trying to accomplish? Are we taking an image? Are we making a map? Or are we making a model? There are 3 different levels of complexity, and they're all going to dictate different levels of effort. Taking a picture is obviously the easiest. The next step up is to make a map, which is something that we can measure and that we can quantify what its error is. And that's compared to a model, which is really going to affect more of our flight pattern and what angles do we need to capture images at to get a nice, pretty model to show people. This particular presentation is geared toward traffic crashes. In a traffic crash, we're almost always trying to create a map that's for measurements and for criminal prosecution. That means that we're going to have to be able to walk into court. We're going to have to be able to give some sort of an error estimation as to what the error is of the map and the error of our measurements are. It's going to be critically important as we're moving forward for this to be adopted in most of our courts. So let me give you a case presentation. This will be a step-by-step example, show you how it is that we're using this technology and how I believe other agencies can use it as well. So this was a traffic crash that happened in a rural part of our city that you can tell this is a Pix4D example. This is kind of the Pix4D map that you would see once you import your data. What happened here is there was a Corvette with a couple of young men in it that were out driving around at nighttime. Of course, they were driving above the posted speed limit with their Corvette. They went through this this cross intersection and didn't realize they were approaching a stop sign. By the time they did realize it, they could not stop, and they hit a vehicle that was traveling southbound through that intersection. They had the right of way, broadsided them, ended up killing both people in that car. This happened at nighttime, as I said, and since this was rural, this was a very dark area of the city. So I'm showing you an area that was dark, and what that would turn out looking like. A little bit closer in, I wanted you to see the flight paths that were flown for this particular mission. So there were, I think, 3 different flights that were done. The first was a nadir flight, which was looking not perfectly straight down. It actually was about a 70-degree angle. But you can see the single grid kind of lawnmower pattern that we're used to seeing back and forth. After that was flown, we flew oblique patterns around both of the vehicles that were involved. And then all the other spaghetti stuff you see in there is us taking some manual imagery, flying through the scene and trying to take some images as we're going toward the vehicles. This is what it looks like once we bring it into Pix4D. So you can see the 2 different flight altitudes that were used. Primarily, I believe this was flown at about 75 feet for the nadir-facing imagery, and then about half that, usually right around 35 feet when we're flying these obliques. There was very few obstructions in this particular case, so we were able to fly a lot lower and keep everything at about the same altitude. All the points that you see at the bottom there are tie points. Tie points just mean that those are pixels that are similar in at least 3 or more images. So photogrammetry is going to tie those pixels together. It's called a tie point, and there tends to be 1,000 or more of those per image. So it's actually a very robust model for taking measurements once we've quantified what our error is. So let's go through the nuts and bolts of how we're going to measure this scene while we're there. That we're going to need to be able to scale this map as well as quantify the error for us to use later. So the first thing we're going to do is we're going to set ground control. Ground control is spread throughout the scene. Typically, we want it to have it on the 4 corners of where we want our map, as well as something in the middle. Our agency typically uses 5 ground control points for most of our scenes. That unless you happen to have a scene, I guess, that has multiple acres involved, you can usually get away with this number of ground control points for, say, a 1,000 by 200 foot scene. Ground control targets are labeled here for you to see. If you look really closely, you can see the little pins where the Pix4D has placed them because I've marked them in the images. But the way we mark this on the scene is actually very simple. We went to Home Depot. We got some circular white furniture movers. We put a little dimple directly in the middle of those furniture movers. We used some double-sided tape, stick them down on the asphalt, and then we label these 1 through 5 for our 5 ground control points. We're going to take our total station, put the tip of our prism rod right in the center of that dimple of the target, use a stabilized prism pole, and then we take measurements to it. That's going to be our control, if you will. That's the known. And that's how we're going to set the coordinate system, and that's how we're going to scale this. You can use a traditional total station with an arbitrary coordinate system, or if you have a GNSS system, you can also use latitude, longitude, and elevation, whichever one you're using right now. But again, this isn't anything super hard. It's more a matter of where you place them and making sure they don't move once you've measured them, so you get them in the imagery. After we've set the ground control, the next thing we want to do is set our checkpoints. So where the ground control locks the model into a coordinate system, the checkpoints are used for us to compare the measurements from the total station with the measurements that are being calculated in the photogrammetry, in the model. They're sometimes going to be very close, they're sometimes going to be very far apart, but we don't know that until we can actually check them with these points. In this particular case, there was a lot of elevation, so we chose 7 different checkpoints. Typically, we would use 5. In this one, we put checkpoints that were at elevation on top of electrical boxes, as well as in the field, up on the roadway, because we really wanted to be able to test the topography and see what that elevation error was. Again, these are evenly spaced throughout the scene. If you can get some vertical ones, that's great. Again, this is measured with total station and the same furniture movers. Once we've collected all of our data at the scene with our total station, this is essentially what the layout is going to look like on a diagram. So you can see the different ground control points and their spacing. You can also see the different checkpoints. Checkpoints, we typically label those by alphabetic letters, whereas the ground control is by numbers, so that way our team can tell the difference between the two. You can see all the actual measurements underneath of the total station there for what we actually measured. This is really all the measurements that are done at the scene. We collect the measurements with the total station, we take the images with the drone, and we're done with taking our scene measurements. That's the amount of time it takes for us to do a scene diagram. So when we get back to the office, we're going to put all of our imagery into Pix4D and we're going to process it. Once some initial processing is done, we'll be able to go in and mark our ground control points and our checkpoints to tell the software where those are located in the imagery. Once that's done, we're going to be able to generate a quality report. Sometimes that's done for us, sometimes we need to ask the software to do it for us. But I wanted to go through a couple of boxes in that quality report to talk about errors and accuracies. So in this very first box, this is at the top of the report, it tells us essentially what camera we were using, what the sensor looked like, but it gives this value for ground sampling distance. So let's talk a little bit about that because I hear this used a lot. The ground sampling distance is the distance between the center of one pixel and the center of the pixel next to it at the ground level. So this is dependent upon the size of your sensor, your focal length, and the altitude at which you're flying. This will change for a given camera at the altitude you're flying at, that the higher you fly, the higher your ground sample distance will be. This is not related to the error or the accuracy of your map. This is far more related to the resolution of what objects you would expect to be able to clearly see in your imagery. So just be aware of what that is telling you. In this particular case, we're at 0.38 inches. The next is all the checkboxes. This is Pix4D's way of showing you how well the project processed. If you have all green check marks like this is, that's good. So again, it's going to tell us how many key points there are per image, how many of our images were actually calibrated, the relative difference between the initial and optimized camera positions, how many matches there were per calibrated image, and then we get this georeferencing where we get this RMSE error equal to 0.026 feet. RMSE error, this is the root mean square error. This is not the error or the accuracy of our map. This is a calculation of the error between where the ground control from the total station, where those measurements were at in three-dimensional space versus where the model from the photogrammetry is placing those same points in three-dimensional space. So those 5 points are never going to match absolutely perfect. There's always going to be a little bit of error between them, and this is a calculation of how much error there is. Next, as you're going through your quality report, you're going to see where they give a mean reprojection error. So just to talk a little bit about that the mean reprojection error, that when you go through your imagery and you're marking points in 2 or more pictures, Pix4D is going to calculate out in three-dimensional space where that point has to exist based on where you pick those pixels in the pictures. So once it finds that three-dimensional location, it's going to reproject that through all of the images that you clicked on, and it's going to calculate out what's the difference between where you clicked and where it's reprojected to, where all those points come together, all those reprojections from all those images come together in space. So the calculate space versus the reprojected location. The difference in this one is 0.17 pixels. So this is a pretty decent number. But again, this is based more on the calibration of the camera as well as how well the user ended up clicking the different images. So what do we use for error reporting? We follow the ASPRS positional accuracy standards for digital geospatial data. This is the heading for the document that I'm showing you here. You can Google this and it's going to show you a PDF document that you can read through. But essentially what we're going to do is we're going to look at the errors reported in Pix4D from our ground control points as well as from our checkpoints. And we're going to use those to figure out what our actual error rates are within our map. ASPRS, the American Society for Photogrammetry and Remote Sensing, has been around since 1934. These standards were created in 1990, so almost 3 decades ago. Then they've been used for aerial imagery. They've primarily been used for manned aviation and those sorts of pictures for aerial imagery. So when we're talking about Google Earth or Bing Maps, the manned aviation flights or the satellite imagery that's been used was how the standards initially came about. In 2014, they rewrote these, and they now provide map class standards that can be used for any sensor or any platform. They're completely sensor and platform agnostic. So it's more about what is the accuracy of your ground control and how does that relate to the accuracy of your map. Okay, so we're going to get in the weeds a little bit here, so don't gloss over on me just yet. So let's talk a little bit about the errors in this. I've just brought in the exact same thing you saw from Pix4D for the ground control points. So you can see our 5 ground control points over here on the left. We have our difference between what the total station says that they should be and where the position was in Pix4D for the model. And there's some differences in all of those. So essentially you've got this fixed model that can't move, and you're trying to make these 5 points fit on these known 5 points from the total station. And it's kind of like all 5 points are on springs, and it's trying to find the best fit for those 5 points, and then it locks it in place. Because it doesn't fit perfectly, there's going to be some error for all 5 of those points, and that's what we're seeing here. So we get it reported to us from Pix4D in feet. That's how I have our total station set is an arbitrary coordinate system in feet, and so that's why it's giving it to us in feet in Pix4D. I now have converted that over to centimeters, and then as we go down towards the bottom, you can see that we have done some calculations for mean error, standard deviation, as well as the root mean square error. So what we're really interested in is the RMSE. So by these standards for ASPRS, here's our root mean square error. Our ground control must be 4 times more accurate than our map class. So in this case, our greatest error is in the X direction. It's at 1.25 centimeters. So we have to be 4 times that. Our map class can't be any less than 4 times that number. So just to keep it simple, we'll just call that a centimeter to keep the math simple. So if we have a centimeter of error, it means that we have to go with a 4 centimeter map class. We can't do anything less than that because of that error rate. So now we're looking at the table for our checkpoints. Again, this is laid out the same way as the table we just looked at for our ground control points. What you'll notice over here on the left is our 7 checkpoints. We have all of the residual errors in the X and Y direction, so that's the horizontal plane as well as the Z axis, which is our elevation. Those are converted over into centimeters, and then over here at the bottom, we can see that the RMSE is about a centimeter, 6 millimeters, and 5 millimeters. So again, by ASPRS standards, this is supposed to be 3 times more accurate than our map class. This is actually better than that, so we definitely meet those standards. So you may stop and ask yourself at this point, well, doesn't that mean that all of our measurements are at least within 1.118 centimeters? No, that's not what this means. This just means that for those 7 points, this is the average, it's not really even the average, it's the root mean square error, which is a slightly more robust calculation than average. This is the error of those 7 points. A point cloud is made up of millions of points. We don't know what the error is for all of those other millions of points. This is just telling us what it is for those 7. So that brings us to our positional accuracy statements. So in what we just saw was the accuracy of our 7 checkpoints. Those are 7 single measurements within a point cloud of 1, 2, 3 million points. We can't possibly measure all of the points in our point cloud to know what the error is over the entire thing. So what we have to do is make a confident statement based on a confidence interval, that this is all going to be based on statistics, that we're basing this on the assumption that the error throughout our map is normally distributed, and that at 95% confidence or at 2 standard deviations, we can report that as a confidence interval. So the math behind this is presented in that positional accuracy document that I showed you earlier through ASPRS. So I'm not going to get into it here, but essentially, the statements we're going to be able to make are that the actual positional accuracy was found to be an RMSE X of the 1 centimeter, RMSEY of the 0.6 centimeters, which equates to positional horizontal accuracy of plus or minus 9.7 centimeters or 3.8 inches at a 95% confidence interval. So essentially, any measurement that I make from point A to point B in my point cloud that's in the horizontal plane, I can say that it is this distance plus or minus 9.7 centimeters or 3.8 inches. If I'm talking about the vertical direction, this is a non-vegetated vertical accuracy, which means that it's over bare earth or over asphalt. It's not over a grassland or over a tree canopy. In this particular case, the actual NVA was found to be RMSEZ 0.586 centimeters, which equates to plus or minus 7.8 centimeters or 3 inches at 95% confidence level. So again, if I'm going to start taking measurements in the vertical direction, I'm going to be plus or minus 3 inches in my measurements. This is the kind of accuracy statement that I can go into court all day long and testify to the error rate of my diagram. The diagram of my map was I'm showing it that way. So is this good enough? Well, it really depends on what you're using it for. For traffic crash reconstruction, plus or minus 3 inches is perfectly fine. Almost all of our calculations are going to be just fine with 3 inches. Now, are we going to be able to get critical speed yaw measurements based on this? Probably not. We're probably still going to measure that on the ground just as we always would. We usually wouldn't even measure that with a total station. So it's not going to change the way we do business when it comes to traffic crashes. Now, when we're talking about crime scenes, plus or minus 3 inches may or may not be good enough. If you need better than that for trajectories or for blood spatter, this may not be the technology for you. What I can tell you is that the more accurate you want to get beyond this, the greater the level of effort. It becomes exponentially more difficult to get better accuracy. So it really comes down to how much time do you want to invest in this, and is it worth putting that time into it, or do you use a different technology? At our agency, we would choose to go use a laser scanner if we needed greater accuracy than 3 inches, and then we would use the drone for everything else. So if we had an outdoor shooting scene, we may very well use a Faro for the inside crime scene, and then we may very well use our drone to get the entire crime scene to show how the actual crime scene fit into the general location. So it's important to know what the use is, what you're trying to get out of it, and be realistic about what kind of error you're expecting. So I always like to put this in perspective, that I hear a lot of people in the industry saying that they can create sub-centimeter maps, or they can create 2-centimeter maps. So based on the ASPRS standards, if you can say that you have a sub-centimeter map, if you have a 1-centimeter map class, you're going to have to be able to provide ground control that is 4 times better than that. So your ground control is going to have to be within 2.5 millimeters. If you're doing a 2-centimeter map class, you're talking within 5 millimeters of error. Again, those are incredibly hard to achieve, if not impossible, with almost all technologies. So just be aware of what people are selling and saying they can do. They may be misrepresenting or not really understanding what some of these standards are, at least through ASPRS. Okay, so now we know what our map class is. We know what our error rate is. This is still back at the office. Now we can start building the rest of our reconstruction. So typically what we will do is we'll go and we'll mark all of our evidence points in Pix4D. You can see all the different tents that we laid out at the scene. We mark all these evidence markers in the picture, and we're able to show them here. This is just a quick screenshot. So with these points, I can now export them out to whatever diagramming software I use. Your agency probably uses, a different program than mine does, although we all tend to be fairly similar. But essentially, I can export this out as an XYZ data set, the same as I would get from my total station, and I can import that into any of my favorite photogram or any of my favorite diagramming software packages to create my wire diagram. So here's what our typical wire diagram looks like. This is what we've been using for years with our total station. This still works just great. I honestly, for a lot of my reconstructions, don't necessarily need all of the other data that comes with some of the imagery. This is really good for me to see how the vehicles hit one another, where they were positioned in the roadway. It's also really helpful for me to see to pick my angles, which way cars are going. So when we're doing speed reconstructions, we need to know what angles vehicles are coming in at. We know what angles vehicles are going out at. I can very clearly see on this which direction each of those vehicles are going. The other piece of that puzzle, though, when I'm trying to do a speed reconstruction, is the drag factor. How much friction is there on the roadway? I can quantify the amount of friction for the asphalt surface. I can quantify the amount of friction going off into the dirt. But both these vehicles went through ravines. They both hit hard on the sides. One of them flipped over. One of them furrowed very deeply going out into this nicely plowed field. We don't have values for that. We're going to have to estimate it. And when I go to estimate that, there's going to be lots of experts who are going to have obviously different estimations than me. So I want to be able to explain to a jury why I chose the numbers that I did. This is actually a more useful diagram when I'm trying to figure out what my drag factors are. That again, we can still see the vehicles at impact. We can still see how all the roadway markings line up with the evidence tents that were put out at the scene. But it's much easier for me to describe how each vehicle acted dynamically as it went through either the canal or the Corvette that hit that utility box and then flipped over onto its top. All of those are going to be drag factors that I'm going to have to take into account, but I can better describe them and I can better calculate out the distance traveled through each one of those different scenarios based on this picture versus the other one. It's also useful for me to be able to show a jury exactly how much friction we're talking about. So in this particular case, we can see that this car was coming off the road going almost sideways. It impacted right here on the side of this canal, spun, and then is furrowing fairly deeply going off into this freshly plowed field off to rest. So this is all going to be important for me to be able to explain to a jury. Again, our Corvette over here goes off the side of the road. It hits this utility box, actually takes the box out, and then it flips over onto its top. So as I'm trying to explain to a jury what drag factors I used, this is a very useful tool for me to help them visualize how much energy would have been expended through each of these different routes. When we talk about data and how much data is actually collected, what's nice about any photogrammetry software, again, this is the Pix4D version, is that we can collect measurements from the vehicle to anything. So in this particular case, one of the occupants of this vehicle was found just upward, I guess, from the vehicle in this particular picture. But if we want to know what the distance was, we can actually calculate that out. We can pick our points in space. But as we pick our points on the left, they're going to show up in the actual images over on the right. As they show up in the images on the right, we're able to refine exactly where we want to take the measurements from in three-dimensional space. So it lets us get a much more accurate measurement. This measurement is still going to be plus or minus some amount of error. But what's cool about this is that we don't lose data. So as we were talking about earlier, where every scene we forget to take a measurement, or every scene we didn't know there was information that was actually there that we find out about later. Someone tells us, oh, that piece of debris was actually relevant that we didn't know at the time. We haven't lost anything. We can always go back. We can still measure it. We still have the same amount of error measuring to it. And we also have all these pictures of it, at least from the drone, that we can show where it existed at the scene. So we're not losing anything. We actually get far more data than we would have had otherwise. So let's talk a little bit about the different deliverables. This isn't necessarily something that I'm taking measurements from. This is more for me for demonstrative purposes when I'm talking to a jury, that I can show the jury this Google Earth image and what this looks like with respect to the rest of the city. Then I can show them this overlay that actually has our scene from the night of the collision. This is nice just so they can visualize it, but we've also had several incidents where we've had multiple crime scenes, and we're able to put multiple ortho photos like this over top of different locations on Google Earth. So we can show the individual scenes and what it looked like at those individual scenes, but then we can overlay that on Google Earth so they can understand the differences in time and space as we're trying to walk them through what maybe happened during a crime. One of the other deliverables is obviously a point cloud. This is where almost all of the work takes place. When we're talking about scene measurements, this is where all of that is done. We can do some cool things with animations and other models, but this is really where most of your work is going to occur in the point cloud. From the point cloud, we're able to create a triangulated mesh. Essentially, the software draws lines between all of those points and creates little triangles and then colors them. And essentially, it becomes a textured model. This is what that looks like. All the points have been shut off, and now we're just looking at the textured model. If we wanted to try and give the jury some perspective of what things looked like, perhaps what a driver or pedestrian or bystander could or could not see. Then the last deliverable we're used to seeing is an ortho photo. So an ortho photo just means that it has been orthorectified. It has been corrected so that you are looking at the image in all places as if you are looking at 90 degrees or orthogonally to the ground. So that's where that orthorectified or orthophoto comes from. In my opinion, these are very useful for demonstrative purposes and for us to explain to juries what happened. But these, again, for me, fall somewhere between a picture and a map. That it's hard for us to. There are errors, there are distortions that occur in this picture as the software is trying to put all the different pictures together with the parallax between where images are taken from. So I don't typically necessarily use this for my measurements. Again, my measurements will almost always come from the point cloud, where I'm actually measuring from individual places in space versus where there could potentially be errors in how this image is being displayed as it's going through that ortho rectification process. So that's what I have for you today. I really appreciate you watching the video. I hope the presentation was helpful and it showed you some of the uses for photogrammetry. If you have additional questions or other comments, please feel free to email me. My email address is there on the screen, and I'm happy to help you or your agency out with whatever it is you might need in the future.